Welcome to another video for Stat 420. In this video, we're going to talk about significance of regression in the context of multiple linear regression, which there's going to be a lot of similarity with simple linear regression, but we're also going to look at the case of nested models as well here. So let me just, oops, I got logged out right at the last moment there. Okay, there we go. So we're first going to talk about the idea of looking for the significance of the regression for an entire model with two or more predictors. So we talked about this with simple linear regression. We can conduct an F-test to decide if there is enough evidence, if there is sufficient evidence that the single predictor we have has at least some linear relationship, is providing at least some predictive power in this model. And we also talked about, in the case of simple linear regression, the F-test and the T-test are going to do the exact same thing. It's really the exact same underlying method. The difference is that an F-test has kind of the structure or the flexibility to take on variability from more predictors, the way it's structured, whereas a T-test is specifically designed, in the case of just comparing one value to one hypothesized parameter. So we can do the same idea with multiple regression, where we're just looking at kind of a variance comparison of this full model with two or more, or however many predictors we want, compared to a null model with no predictors added. So our null hypothesis here is that at least one of these predictors has some kind of linear relationship with the response, right? The null hypothesis is that none of them do. The alternative is that at least one of them does. So if the null hypothesis is true, then all these predictors that I've added are not doing anything, or I guess I should say, under the null hypothesis, the only thing that I'm going to get from these predictors is some random chance variation explaining, meaning that, just by the fact that I take a sample, I might see a little bit of correlation, but it isn't actually an underlying effect. It's just because that's what happens when I take a sample, is I'll get a little bit of, trivial correlation for any of the predictors that I add, but nothing that represents an underlying effect. The alternative is that at least one of these predictors does something. At least one of these predictors does have a linear relationship with the response variable. Okay, so we're going to look at this in the context of this data, which is looking at if there's a correlation between professor-student ratings and different characteristics about the professor or about the class that they were teaching that semester. And so kind of the catchy part of this is that one of the predictors they looked at is beauty. So they had 6 undergraduate students actually rate these professors in terms of just like how beautiful they were. I don't know exactly what the prompt was, but they call it beauty in the paper, I guess. So let me get myself out of the way. That said, there's also some other variables about these professors as well, and this paper did some modeling to see if there's any kind of way that we can model student evaluation ratings for professors based on different characteristics about them that honestly shouldn't matter in their ratings, hopefully. So we're going to focus on the beauty predictor here first, but we're also going to have some other predictors in this model as well. So notice that we have kind of the average beauty score for the professor as a predictor, the professor's age, and the number of students that professor had in each class. And then we're using that to try to model the average evaluation score for each class that professor taught. So our regression looks like this, and again, we can kind of see these individual p-values for each predictor. So it's saying that given 2 professors of the same age with the same class size, this is how much effect we see from beauty, and this is how confident we are that this is not 0, that this is actually something going on. So the fact that the p-value is low is telling us that we have pretty strong evidence that there's at least something going on here. Now, it doesn't tell us how large the effect is. We'd have to kind of look at the slope and judge it contextually. Or, we could do a solo model and look at R² as well. But for now, these are just kind of, solo predictor information in terms of, controlling for the other predictors. This is how much we see each predictor kind of adding. We're more interested down here in this F-test result. So the F-test is looking at all of this and saying, do we have evidence that that at least one of these predictors is probably doing something? And the idea here is that if I keep, if I add enough predictors, I'm probably going to get a relatively low p-value every once in a while by random chance, right? So if I add 20 predictors, I would expect around one of them to have a p-value below 5% by random chance. Maybe none of them, maybe two of them, but the more predictors I had, the more often something like that is going to happen by random chance. So that's why it might be helpful, instead of looking at these individual p-values, but to actually have kind of a like a singular p-value representing the significance of the model and how confident I am that there is at least one thing in here that is working. So we can look down here. Our p-value is 0.0004997. So that means we have some good evidence against this null hypothesis over here in favor of the alternative that at least one of these predictors probably does have some kind of relationship here. Now, kind of undergirding this, all of our this summary output is going to give us is the F statistic, the degrees of freedom associated with that test that was done, and the p-value result. What's going on behind the scenes is some other calculations here, kind of this decomposition of variance, where we have the amount of variability being explained by the regression, the amount of variability that is not being explained by the regression, and the total amount of variability in the response variable to begin with, right? So y sub I minus y bar is telling us variability, just kind of raw variability in the response. Y sub I minus y hat is what isn't getting explained. Y hat minus y bar is what is getting explained. It's kind of the improvement that I'm adding from just using y bar as a universal best guess for the response variable down the line. Now, an F-test is also going to take these raw variances and divide it by a degrees of freedom value. And you might just kind of think of this as, forget the -1 for a second and just think of it as number of parameters. So for each parameter that is involved here, I'm going to divide this raw variance by that total number of parameters being estimated. The error is going to be the difference between my total number of observation minus those parameters, and the total is just going to be approximately the number of observations in the data to begin with. So by doing that, what I'm kind of doing is seeing how much variability is explained per parameter in comparison to how much variability is explained per observation. And I'm comparing that ratio over here as kind of my F-test. Or I guess, I can honestly just point over here for a second. I'm comparing that ratio of amount of variability explained per parameter divided by, this would be the unexplained variability per difference of observation minus parameters. So it's okay if you're not like completely clear why this calculation does exactly what it does, as long as you know this big picture of this is a ratio, and it's telling us how much more variability we explain with the added parameters, with the added predictors, compared to what's not being explained otherwise. So we can also kind of do some selective matching. I just put one example up here for reference because it's not really necessary to do all of them. But right, like if I take this data for a second and I find my fitted values minus the average value for the response, and I square those differences and sum them up, notice that I get 5.17. And that's going to align with what's going on in my ANOVA table. So if I do an ANOVA and compare these two models, if I compare the null model to the full model, I would get this ANOVA table that's being generally described over here. And I can kind of verify any value in this table that I want by doing, or actually it's already right here, by doing the relevant calculation for that cell. So I just did this kind of for demonstration that this isn't, again, it's not magic. It might feel like that, but these are real calculations being inputted that we could verify if we wanted to. So we already kind of did this, but let's make a formal conclusion here on the significance of this full model. Our p-value is quite low, so I would say we have, or actually, let me start with kind of our standard language. I'm going to say we reject the null hypothesis, and then I'll just kind of add some context here. We have sufficient evidence to conclude that at least one of these predictors has a linear relationship with evaluation score. Right, so I could have written a little bit more detail there if I wanted to. Right, I could list the predictors. I could say like that at least one of these predictors, average beauty score, class size, and age, has a linear relationship with average evaluation score. But that's probably sufficient there. I'm judging that based on the fact that my p-value is low, and I mean, we don't have an alpha value listed, but I mean, what alpha value would I reasonably choose that's lower than that, right? Am I going to set my alpha to 0.0002 or something? Probably not. So if I'm using, say, like an alpha equals 0.05 or 0.01 or whatever, so I'll just say set alpha equals 0.5, then I can make this decision. And in general, something I'll kind of remind is, you know, the field is kind of moving away from these very binary decisions in hypothesis testing. This is a very school thing to do, but it's not necessarily a very realistic thing to do in your industry. And that's because nobody is necessarily going to tell you what your alpha level should be. It's really up to you. And so the truth is you're just going to be, you know, getting some p-values in different contexts. And it's really up to you to just interpret what that means. It's saying that if the null hypothesis is true and none of these predictors have a linear relationship, then I would see a result like this or more extreme this percent of the time. So, you know, you can kind of judge from that, like, you know, that's pretty good evidence that there's something going on, whether or not you have set an alpha level beforehand or not. So I think just be in the habit of looking at a p-value and interpreting it for what it is without being really hung up on, but what's my alpha level? Like, how do I know what to do? Well, we know how to interpret a p-value, you know, just as it is too. Now, the significance of regression gets a little bit more interesting when we think about the possibility for doing nested models, right? So, you know, we can kind of look at that example, and something we might notice here is that we have one predictor that seems to have a pretty strong relationship, right? Like its individual p-value is quite low. If we did a solo model, it would be even lower. But certainly, even when we're controlling for these other two things, it's still quite low. And we might be kind of wondering about these other two, where it's like, well, these two didn't really show much. Like we didn't find much at all evidence that they're adding anything to this model when we already had the others in it. So maybe we can do a test for significance between a model with one predictor, beauty, and a model with all three of those predictors to see if there's a significant amount of variation being explained when we add those two predictors in. So that's what's going on here. Is a nested model is where I have a model with some number of parameters and another model with a subset of those parameters. So not all of them, like, so everything in the smaller model is in the bigger one, but there's things in the bigger one that are not in the smaller one. So that's what we call it a nested model, is it's a subset of the larger model. So if we're kind of representing this mathematically, we might say that we have, let's see, p parameters, p minus 1 predictors, and this one has q parameters, q minus 1 predictors, and q is less than p. So as long as that's the case, that's how we kind of mathematically represent this. And the null hypothesis is that these added predictors in the full model are not doing anything. So from b sub q to b sub p sub 1, so basically this difference, right? So where I stop here and where this one ends is kind of these extra predictors. And the null hypothesis here is that these don't have a linear relationship. The alternative is that at least one of this set of b sub q through b sub p minus 1 has, or I'll say is not equal to 0. Okay? So again, our ANOVA table is really the same thing. The only difference here is that the degrees of freedom adjust a little bit, especially, well, on this line and this line specifically. And so again, we kind of talked about this is essentially, we're essentially dividing this by p. However, we make an adjustment based on the number of estimated parameters. So there's kind of some background going on. If you understand how unbiased statistics work and we're measuring variance or just measuring variability in general, there's often going to be kind of this error correction for each parameter that's being estimated in the measure. So for each parameter being estimated over here, we kind of do an adjustment with that minus part. But anyway, this kind of the same logic going on here is we are creating some kind of ratio to compare the difference. So the predictive power of those BQ through BP minus 1 parameters compared to the full to see how much groundwork is really being made up by that set of predictors. So we can do this again with the professor data where we have a full model with those 3 predictors that we already saw, and kind of a smaller model where we're only going to use the beauty predictor as our only predictor here. So in that case, we can run an ANOVA to compare them. Now notice here, this is where it gets tricky, is I can't just run the summary of each of these models separately and look at the F statistics and be able to tell something from them individually. And that's because both of these models are running an F test in comparison to the truly null model, the model with no predictors at all. So I can't use that exactly without kind of manipulating these values in some other way. So what I'm going to do here instead is use the ANOVA function, where I can define these 2 models and then plug these 2 models into the ANOVA function to produce an ANOVA result with an F test. And something that we'll notice here is that our p-value comes out to 50% when we compare this smaller model to the full model. So that's telling us, assuming again our alpha is not above 50%, I don't think it would be if we just set alpha to like 0.05, we are going to fail to reject the null hypothesis. We do not have sufficient evidence. To conclude, the Fuller model has, I'm going to write this a little bit differently than I did before, just to kind of make the point that this wording works as well. Has more, I'll say, linear predictive power than the small model. I could also say we do not have evidence that the age beta is different from 0 or not equal to 0, or that the class size parameter is different from 0, that beta. That's kind of a more awkward way of probably phrasing that. But something to this effect here, right? That these 2 predictors, we don't seem to have evidence that these 2 predictors are doing anything for this model, in that if these are our choices, then we should probably just stick with this one and drop the other 2. So an F-test for regression in a nested case can be really helpful for directly comparing 2 candidate models and deciding if we're making up any ground by adding this extra set of predictors, whether it's just 1 predictor, whether it's more predictors. We can kind of test if those predictors are adding anything to our model. Now, this does not change what we're going to see later in the course, and that is model fitting, where when we're doing model fitting in general, this is not the only criteria that matters. It's not just, well, do we make it any farther by adding these predictors? There's also going to be a question of kind of variable suitability, and is this worth it? Like, is this giving us enough predictive power that we'd like to add complexity to the model, and those kinds of questions. So I just kind of mentioned this as one thing to keep in mind, but it's not the only thing to keep in mind for model fitting. And one other thing that I'll mention. So I do want to kind of compare this 50% to the 25% and the 85% that I have over here. So notice how this question of, the p-value for whether age is actually a linear predictor after adjusting for these other 2 things, after controlling for these other 2 things, gives us a p-value of 25%. Even though the F-test for significance of adding these 2 predictors is up to 50%. And that's because this test is going to account for the fact that I have two predictors and not just one. So if you think about the likelihood of getting two predictors such that at least one of them is below 25%, that's going to be about 50%, right? So if you think about the likelihood of getting, this might be a confusing example. I was going to say of flipping a coin twice and getting two heads in a row, right? That can happen. But if I do that coin toss twice and then I do another coin toss twice and I ask the question, what's the chance that one of those two coin tosses ended up with heads twice in a row? Well, now the probability is going to go up. So that's why an F-test is accounting for the fact that I do have two parameters that by random chance could get a lower p-value. So it's not going to be as low if we're accounting for both of them as we are if we're just looking for one at a time. So I'll just mention that in case that comparison is kind of helpful to make there.